Welcome to Empowered Learning. In this video, we are going to discuss the alternating series test as one of the tests that we use whenever we deal with series in calculus to be able to tell whether that alternating series is going to converge or not. And so if you've been watching my previous videos, at this point, you've probably already watched the integral test video, the one about the comparison test, where we talk about the direct comparison test as well as the limit comparison test for series, as well as the remainder estimate theorem for the integral test as well. And so one of the things that has been in common with all of these tests is that we've dealt with series that have had the following three characteristics here. Okay, so one is that each function or each sequence that makes up the series had a corresponding real valued function, or a function with domain that would be something other than the natural numbers that has been continuous. We see here that all the terms in the corresponding series, thus all the terms in the sequence that made up the series, are positive, and the series terms are decreasing. So that means if I was going to list out the sequence of numbers, then that means that every subsequent number is a number that's smaller than the one that comes before. Okay, so we've basically looked at these tests, and all these tests have dealt with corresponding sequences that form series that have these three properties in it. So what we're going to do now is we're going to discuss a test that will show us how to deal with series where some or all the terms of these series are negative. And one of those tests, of course, is called the alternating series test. So the test specifically deals with series where every other term is of opposite sign. Okay, so for instance, if we had, let's say, -1 raised to the n, if we had this particular sequence, then the sequence of numbers here, if I let n equal 1, then -1 raised to the +1 is just a -1. -1 raised to the 2 would be a +1. -1 raised to the 3 would be a -1. -1 raised to the 4 would be a +1, so on and so forth. Okay, so this is a simple alternating sequence here. The main thing is that whatever sequence it is that we're dealing with, we're going to have every other term in the sequence be negative. Thus, if we were to add all of these, numbers up together, then of course every other one, as we add things up together, would be negative as well. Okay. So here, if we allowed our sequence to be some -1 raised to the n-1 or n+1 or n, this portion here is just to do the alternating sign times some sequence b sub n, or particular number in a sequence b sub n, where b sub n values will always be positive, or non-negative, I should say, hence expressing b sub n as the absolute value of a sub n. Then we are considering corresponding series that will be like this, okay, which we could also rewrite, and I'm just going to write it in this form here. Okay, so we're actually we're looking at series here that have this particular profile, and we're going to see what are some of the things that has to be characteristic about an alternating series like this in order for it to be able to converge. And so that's what we're going to talk about next. So the alternating series test says that if we are considering an alternating series of this type, where of course this -1 raised to the n-1, or it could be, just -1 raised to the n, or -1 raised to the n+1. That part really doesn't matter. As long as it has something in here that makes the signs alternate for each term, And of course, this b sub n here is going to be some positive value, depending upon what value of n that we use. And if we were to, list out the terms as we would, add these things up, of course, it'll look like this. We know that a series of this type is going to be convergent if it satisfies these following two properties here. So, these two conditions. The first condition here is that the current value in the sequence is always going to be a number smaller than, or at the very least equal to, the number that precedes it. Okay. So, in other words, if we start listing the numbers in the sequence that sort of helps to make up this series here, this number is going to be larger than the next one, which is going to be larger than the next one, which means that as we list more and more numbers, the value of those numbers tend to decrease the more we list. Okay. The second thing is that this b sub n, whatever it is going to be a function of the natural numbers. If we take the limit of that particular expression as n approaches infinity, it's going to go to 0. And of course, that's another way of saying that as we list our numbers here, it's going to get lower and lower and lower, but it's going to get lower to the point to where eventually it goes to 0 if n keeps on increasing. So we know that the any alternating series, it may not necessarily on its own be convergent, but if it has the properties of having each number in the list from the sequence b sub n being smaller than the next one, and we take the limit of the nth term of this particular sequence here, and it goes to 0 as n approaches infinity, then we know that this alternating series test will converge. And so we say here that it's going to converge conditionally. Okay. And I'm actually going to make a separate video about this whole concept of absolute versus conditional convergence. Right now, we're just going to say that an alternating series type of series will converge if it has these two properties. Okay. Now, to sort of illustrate this in a simple example here, let's look at this particular series. Okay. So let's look at this series. And so what this actually is, it is the alternating harmonic series. Okay. And so we see here, if we did not have this -1 raised to the n, it would just be summation from n to infinity of 1 divided by n, which we know that is the harmonic series, and the harmonic series always diverges. Okay. You could also think of it as the harmonic series is just a p series where p is equal to 1. And for those of you that aren't familiar with that, this is what the p series looks like here. And so this would be equal to this whenever p is equal to 1. Okay. Now, so in general, we know that the harmonic series, this diverges, but the alternating series will converge because of this fact. Okay. So if we're considering this, then our b sub n is going to be the 1 divided by n. And of course, if I started listing out values of b sub n, then of course, first I would have 1 divided by 1, then 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 5, so on and so forth. And we know that the more numbers I list, the smaller the numbers get here. So of course, this is when n is equal to 1. This is n is equal to 2. N is equal to 3. so on and so forth. So the more numbers we list or the higher values we plug in for n, the smaller the actual b sub n number gets. Okay. So the second thing is that if we take the limit of b sub n, which is the same as taking the limit as 1 over n, then of course we know 1 divided by infinity in terms of limits just means that we're dividing 1 by an infinitely large number, which goes to 0. So although the harmonic series, the pure harmonic series, diverges, we know that the alternating harmonic series converges. Okay. Now, you're probably wondering, well, why is it converging? Because it's alternating. And so I want to talk more about this in the video that I make on conditional convergence versus absolute convergence. But essentially what's going on is this. So with an alternating series, we can actually split the sum we can split the sum that we're doing of all the numbers into the negative terms and the positive terms. Okay. And so to make this real simple, if we took all the negative terms, which I'm just going to call b sub n minus, and we were to add them up, they would be approaching negative infinity. If we took all the positive terms in that series, which is going to call b sub n plus, and we added those up, they would be approaching positive infinity. And if we combined these two together here, then theoretically speaking, if we took a negative infinity and added it to a positive infinity with the sums, technically in terms of limits, you can't really do this. But if the negative infinity and the positive infinity that we're talking about has relatively the same size, then of course we would see that the difference in between these should be approaching 0. Okay, which means that it's converging upon that number 0. So that's essentially what conditional convergence is trying to get across here. Okay, and the alternating harmonic series is a good example of that. All right, so now that we've talked about the alternating series test and we've seen a very simple example of how it works, then the next thing that we want to do is figure out, all right, well, what is going to be, or how are we going to estimate what the actual sum of an alternating series would be if we figured out what's going to be the sum of this particular series for the first n terms of it. Okay, so if we assume here that the infinite series of this alternating series that we're dealing with is going to be some value s, so if we assume that that's the sum, then if this particular series satisfies both of these conditions here, which is essentially the conditions that we had to say that the alternating series converges, then we know that the remainder, which we're going to call r sub n, can be calculated by doing the following. And so we'll just take the absolute value of whatever the actual sum should be minus what is the sum of the first n terms. And we know that whatever this value is, it has to be less than or no more than, I should say, whatever the value of the b sub n plus 1/th term would be. Okay, so to make that real simple, let's say if we wanted to find the first one, find the sum of this particular series here for the first 100 terms, then of course the last term that we would be adding up is b sub 100. And then, of course, after that, we'll have the 101st number in that particular sequence that we'll be, adding up and whatnot. And what we're saying here is whatever value this particular number is, the remainder of whatever, how much we're off from what this actual value is, it can't be any more than this particular value here. And that makes sense because if we were to talk about the 101st term and the 103rd term, 102nd term and 103rd term, okay? Here, remember that these values here are smaller than the 101st, okay? So if I keep on adding, stuff up here, can't be any more than this because this is going to be the largest value out of the list of values that you have left here to add up if you're going to do an infinite amount, okay? And so here again, I have this translation. It says, for a series that satisfies the conditions of the alternating series test, okay, the size of the error between the nth partial sum of the alternating series, and that's like this situation here if I let n equal 100, and its infinite sum, which is what the s is here, is no larger than b sub n plus 1, which is this value here. That is to say the absolute value of the first neglected term in the infinite sum of the alternating series that is truncated after you get the first 100 terms added up, okay? So that is an estimation of that. And so what this essentially lets us know is that if we know that we have an alternating series that converges and we just wanted to add up the first n terms of it, then whatever the value of the n plus 1th term is, we know that we won't be any more than that much off from what the actual sum of that particular series would be. And so that's essentially what this particular theorem is trying to communicate to us. So for our first full example here, we want to test to see whether the following series that we're given is going to be convergent or divergent, okay? And so we are given this series here in this form of just, listing the terms. We can see because every other term that we're adding up is negative, this is going to be an alternating series. And since the first term is positive, the next is negative, and then, so on and so forth, the n plus 1 here in the exponent would suffice. We could also do n plus 1 here in the exponent, and it would also work as well, okay? But I just chose to do n minus 1 here. Now, of course, we see in the denominator here, we started off with 2, and then of course after that it goes up by 1. So of course if I'm starting here at 1, and of course 1 plus 1 is 2, and then of course if I change this to 2 here, then 2 plus 1 is 3. So we see why we would have this 1 divided by square root of n plus 1 as essentially the b sub n term, because we could look at this as summation n equals 1 to infinity this times b sub n, where the b sub n is going to be the sequence that has all positive terms, and of course 1 divided by square root of n plus 1 has all positive terms in it, because we know square root of n plus 1 will never be able to be negative, and since n starts at 1, it won't ever be able to be 0 either. And of course 1 is always positive, so a positive number divided by a positive number is positive, okay? So if we let b sub n be this 1 divided by a square root of n plus 1, then one of the things that we see is that n plus 2, 1 divided by a square root of n plus 2, which can be rewritten like this, is going to be a quantity that's going to be smaller than 1 divided by a square root of n plus 1. Because again, the denominator here, and I'll just use this as a quick example, the denominator of square root of 3 is going to be bigger than the denominator of square root of 2. So if you take the same number divided by a bigger denominator, you get a smaller number. So what we're essentially saying here is that all the terms, or all the numbers of this particular sequence here, as n gets higher and higher, the value of B sub n gets lower and lower. So it's ultimately decreasing. Okay. So that was one of the properties that we had to have for an alternating series to be able to converge. The other thing is that if we take the limit of this particular sequence, the 1 divided by square root of n plus 1, we see that after we do some working out here that it ends up going to 0 here, okay? And I kind of took the scenic route in doing this to try to keep it more along the lines of having this 1 divided by square root of infinity. But I could have done this limit differently and it still would have came out the same way. So at the end of the day, we see because this particular series, and this is just a compact form of what this list of numbers here that we're adding together ends up being, we see that because it has the property that this 1 divided by square root of n plus 1, as n gets higher, the value of that particular expression gets lower, and because the limit of this as n approaches infinity goes to 0, we know that that alternating series will converge. And again, what that basically means is that if we take all the negative terms of this particular series, add them up, it'll be approaching negative infinity. If we take the positive terms of this particular series, add them up, they'll be approaching positive infinity. And when we kind of bring those two things together, they'll kind of be working against each other to go towards 0, okay? All right, so this next example is going to show you what it looks like whenever we have an alternating series that fails the alternating series test, okay? So again, this time we actually have the series in its summation compact form, and we see what it looks like whenever we actually list those numbers out. So here we see that the B sub n part is this rational function here, or rational sequence, I should say, here. And if you note, if we were to list out what these numbers would end up being here, we see that as n gets larger, the numbers get larger as well, okay? So the problem, just to start off with, is that here, this is when n is 1, this is when n is 2, and we see that these numbers here, as n gets larger, should be decreasing, but we see that actually they increase, and we see that there will be no stop to it, okay? Now, sometimes we can have functions to where sequence-wise, they can start off low and increase like this, and then come back down like that. And that's what we mean by ultimately decreasing. But we see that this particular rational sequence here is not going to do that. It's just going to keep, getting bigger and bigger and bigger and bigger and bigger. Okay. So that alone lets us know that this particular series here is not going to be convergent by the alternating series test. Okay. But I go a step further here and I show you that if we actually take the limit of this B sub n part here, and of course we rewrite everything and make it look nice. And here all I did is take the numerator divided by 1 divided by n, do the same thing in the denominator here. And that's how I got the next step there. So I'll go ahead and write that in. So if I had that, multiplied it like this, then what I would end up getting is what you see here. And of course, following my limit laws, I'll eventually be able to take the limit of these two terms here by just plugging in infinity. And we know that 1 divided by infinity from a limit standpoint approaches 0. And of course, that just leaves us the 3 and the 2 here. And we know that 3 over 2 is not equal to 0. So we have not met the condition here where the limit of B sub n as n approaches infinity equals 0 here, because we have 3 over 2. So because of that, we see that the second condition is violated as well. So no matter how we try to look at it, we know that this particular alternating series here will be divergent because of that. All right, so as our third example, we're going to look at this particular series that we looked at in our first full example again. And what we want to do now is determine how many terms of this particular series need to be added in order to find the sum of the actual infinite series within an error of 0.0005, okay? And so here, and I guess we could read this as 5 10,000ths, you know, if you want to be proper about it. And so here, the main thing that we need to remember is that we know that if this particular series here converges by the alternating series test, then whatever the remainder is, of course, this is what the remainder would be, where this S represents the actual sum of this particular series here, and S of n would be the sum of the first n terms of it. If we took the absolute value of it, this quantity would be no more than the value of the term b sub n plus 1, okay? And so whatever this b sub n plus 1 looks like, whatever it is for whatever value of n what we're talking about, we would have to ensure that whatever this absolute value of S minus S of n is, it's not going to be more than this particular number here, okay? So all this stuff that I'm basically stating down here is basically getting to this point here. And so we see that whatever the remainder is, it's going to have to be something that has to be no more than 5 10,000ths, okay? And so we just need to find the value of n such that we satisfy this inequality here. So to force it to actually be within that, I'm going to drop the equal to part of the less than or equal to and just make it less than. So whatever this is, its value is going to have to be less than 5 10,000ths here to be able to make that happen. And so we know that since the b sub n part of our series is just this 1 divided by square root of n plus 1, we know that b sub n plus 1 is wherever we see n, we replace it with n plus 1. And so, of course, from here, you can see we're just doing the math for this. This ends up being 1 divided by square root of n plus 2. We translate this decimal point 0.0005 as the fraction 5 10,000ths, which is the same as 1 over 2,000. And then, of course, it's just a bunch of algebra from that point. And we eventually get to a value of n having to be greater than this 3,999,998. Okay, so we would have to add up 3,999,998 terms. We have to add up more than that for us to be able to do it. Okay. So I guess the next term would be the 3,999,999. Okay. So that would actually be it. So the answer to this is that n would actually have to be this number to ensure that whatever this is, it would be within this particular number. Okay. If we had the situation that we want it to be exactly 5 10,000ths or more, then we would include this particular number. Okay. So it all depends upon, do you want to be within it or do you want to be at least? Okay. And if we go back to this problem here, remember this says that we want to be within an error less than. So that's why here, even though our alternating series estimation theorem had the less than or equal to I had to get rid of that here in doing this problem. Okay. So I hope that makes sense to you. All right, so with that being said, this concludes the video that I have on alternating series and the alternating series test. Of course, the video that you will probably want to watch if you're watching this in order would be the video about absolute convergence versus conditional convergence. And then after that video, you would want to watch the one that deals with the ratio and root test. Okay. And if you want to see more examples of how we deal with alternating series, you could watch the ratio and root test because you're going to see some of those series that we deal with in that will also be alternating series as well. And so I'm going to have some examples thrown in there. So again, if you want to see more practice on, all right, well, how do you deal with alternating series using the alternating series test, then you can watch that ratio and root test video. All right, so plan to see you in those videos. Take care.